Hi guys, followings are the summary of today's video. This video's topic is CG effect on braking and acceleration. But first, I will give you a quiz related to braking and acceleration. What is the quiz? Here we have a quiz. Which brake should keep its function for the entire braking process if you choose only one brake among four? Figuring out the answer to this quiz, you will have a chance to think about the important effects of CG related to its height and horizontal location on braking and acceleration. And we will have a discussion on why does a car tend to rotate at braking and acceleration. Then we will explain what are the effects of CG location on braking and acceleration, effects of vertical location, effects of horizontal location. Finally, I will explain where is the best CG location of a perfect car. I picked up this slide from my previous video. As I explained, front tire braking force and the vertical reaction force are bigger than those of rear tires because of weight transfer we have discussed already. By this reason, front brake capacity is designed always bigger than the rear one to endure this transferred weight here, like this manner. It looks like no problem at all if we design the front brake capacity bigger than the rear one. But ironically, the real problem exists at the rear wheels because the vertical reaction force reduction here due to weight transfer bring about the brake force reduction at the rear wheel also. A weaker brake force at the rear wheels can cause a serious safety problem. We will discuss this in detail in the quiz slide. Please remember, braking forces are produced differently at each wheel, relying on individual friction coefficient multiplied by also individual vertical reaction force. Of course, we have no braking force at all if either friction force coefficient or a vertical reaction force is equal to 0. Here we have a car on the road which has a straight lane, and there are large and deep swamps in both sides of the road. And also alligators are living in the swamp. Here we have alligators. Assuming that the driver found a deer all of a sudden and smashed down the brake pedal. Unfortunately, only one brake is allowed to be available among four. Which brake should keep its function during the entire braking process? There is a driver alone in the car. Oh, alligators are waiting for something. I hope I'm not on their menu. Let's analyze our case one by one. Our first case is this. A front right brake with a red color is alive only. Then what will happen at the panic brake? As you see, we have a CG location here. At the braking, front right wheel won't move because its brake is alive. Then a car weight produces the moment with the moment arm length L1. At this moment, try to turn the car. about the vertical pivot axis passing through the center of front right tire contact patch here. Because the CG is on the longitudinal line, parallelly placed moment arm length L1 apart from the longitudinal tire center line. This is tire center line. This is a longitudinal center line of a car. So we have moment arm length L1, this much. This situation becomes catastrophic disaster. Car tail here likely past the car front end. As a result, car gets unstable and could be rolled into the swamp. Of course, alligators are very interested in this accident. Therefore, I don't like this case. This is our second case. A front left brake with a red color is only alive. Then what will happen at the panic brake? As before, we have a CG location here. At the braking, a front left wheel won't move because its brake is alive. A car weight produces the moment with moment arm length L1. This moment turns the car about the vertical pivot axis passing through the center of front left tire contact patch. Because CG is on the longitudinal center line, parallelly placed moment arm length L1 apart from the longitudinal tire center line here. This situation also becomes catastrophic disaster. Car tail passes the car front end in this manner. And the car may roll over into the swamp like this. Of course, alligators are very interested in this accident, so I don't like this case either. This is our third case. A rear right brake with a red color is only alive. Then what will happen at the panic brake? As before, we have a CG location here. At the braking, rear right wheel won't move because its brake is alive here. Then a car weight produces the moment with the moment arm length L1. This moment turns the car about the vertical pivot axis passing through the center of rear right tire contact patch. Here. Because CG is on the longitudinal center line, parallelly placed moment arm length L1 apart from the longitudinal tire center line here. This situation will end up with a safe stop because rear brake is alive. Car tail doesn't pass the car front end, and the direction of car heading doesn't change too much. Alligators are not interested in this accident because nothing added in the swamp. This is our fourth case. A rear left brake with red color is only alive. Then what will happen at the panic brake? As before, we have a CG location here. At the braking, rear left wheel won't move because its brake is alive. Yeah. Then the car weight produces the moment with the moment arm length L1. This moment turns the car about the vertical pivot axis here, passing through the center of rear left tire contact patch. Because CG is on the longitudinal line here, parallelly placed L1 apart from the longitudinal tire center line here. This situation will also end up with safe stop. Car tail doesn't pass the car front end, and the direction of car heading doesn't change too much. Alligators are not interested in this accident because, again, nothing added in the swamp. So, what's the answer to the quiz? We all know that a front brake is not the answer. Then the answer will be one of two rear brakes. Which one? Answer is that rear left brake, case 2, should be alive during entire stop. Because the moment produced by a car weight is smaller compared to that of case 1. Why? At first, L1 is equal to L2 in the absence of driver. If this driver is absent, L1 is equal to L2. Total car CG location, including driver, moves more to the left side. Therefore, moment arm length L1 gets bigger than L2 here. As a result, the moment of case 1 is greater than that of case 2. This one is bigger than this one because moment arm length is bigger here than moment arm length L2 here. Therefore, case 1 is more unstable than case 2 because of bigger yawing moment. So, the answer is case 2. Rear left brake should be alive during the entire stop. Let's investigate two more cases. This is our fifth case. Both of front two brakes with the red color are all alive, while both of two rear brakes are all dead. We have to know that friction coefficient is different at each tire contact patch because friction coefficient is the function of tire and road surface properties, having variety of spectrum. Therefore, brake forces are different at each side, even when vertical reaction forces are the same at both sides, because friction coefficients are different each other. Then, let's continue our question. What happens at the panic brake? Assuming that right hand friction coefficient is larger than that of the other side, a car tends to rotate clockwise. As you see, we have CG location here. At the braking, car weight produces the moment with moment arm length L1 here. This moment turns the car about the vertical pivot axis, passing through the center of front right tire contact patch, because CG is on the car longitudinal center line here. Parallelly place the distance L1 apart from the longitudinal tire center line here. I hope you can find the small dot here. This is the center of rotation. This situation may become catastrophic disaster. Car tail passes the car front end and roll over into the swamp. Of course, alligators are very interested in this accident. This disaster always happens when the moment produced by the car inertia due to braking is larger than the moment produced by smaller braking force among both sides. As you can see, this force is smaller than this one. So the moment produced by this moment is counterclockwise, should cope with this moment produced by the car, this moment. So we can be sure that the moment produced by braking force should be larger than the moment produced by car inertia, this one. This is our sixth case. Both of rear two brakes with red color here is all alive, while both of front two brakes with blue color here are all dead. What happens at the panic brake, assuming that right hand friction coefficient is larger than that of the other side? A car tends to rotate clockwise. As you can see, we have a CG location here. At the braking, car weight produces the moment with the moment arm length L1. This moment will turn the car about the vertical pivot axis, passing through the center of front right tire contact patch. Because CG is on the longitudinal line here, parallelly place the distance L1 apart from the longitudinal tire center line here. This situation will end up with safe stop, and the direction of car heading doesn't change too much because rear brakes are all alive. This result is much safer than that in the previous slide. Let's think about the car behavior due to braking force. Weight transfer changes the car attitude. Pictures in the slide shows the vehicle attitude for various cases of the ride height according to the magnitude of brake forces. A brake force is increasing in this direction, here, in this direction. A ride height at the rear wheels, here, increase bit by bit in this direction, while those at the front wheels decrease bit by bit in this direction in proportion to the magnitude of total brake force. brake forces at the rear wheels, decrease bit by bit in this direction, while those at the front wheels increase bit by bit in this direction in proportion to the quantity of transferred weight. Let's investigate what happened at the rear wheel in the braking. The higher CG height results in series of undesirable effects to make the car performance deteriorating. The bigger weight transfer, the higher ride height, and the weaker tire grip, which cannot produce the stable brake forces at the rear wheels. The higher CG height makes both of braking time and distance longer because you have to relieve the brake pressure at the relatively earlier time compared to the lower CG height. Otherwise, rear wheels lose their tire grip. Therefore, CG height should be as lower as it can. Let's think about the CG location on the horizontal plane. There are two cases about the CG location in the horizontal road surface in this slide. In the first picture, CG is located on the longitudinal center line of a car, here. In the second picture, CG is located some distance apart from longitudinal center line of a car. The longitudinal center line here and the CG location here. So there is an offset between two lines this much. A friction coefficient mu changes by factors of road surface. For example, wet, snow, roughness, etc. And the tire, for example, material properties, temperature, tread wear, internal pressure, etc. Those factors are not the same at each tire in the car. When braking is applied, car has a tendency to rotate on the vertical pivot axis at the tire contact patch center, having largest friction force. This is the larger friction force here. In the second picture, this is a larger friction force. Tendency to rotate gets larger if CG location has a bigger offset from the longitudinal center line of a car. In the first picture, there is no offset here because L1 is equal to upper L1 is equal to lower L1, so the distance is the same. Therefore, the CG location in the horizontal surface is located at exactly on the center line of a car. In the second picture, the CG location has an offset this much from the center line of a car. So the moment, the yawing moment in the second picture, this one, is bigger than that of the first picture, this one. the car starts to rotate when the moment by inertia force gets bigger than the moment by smaller longitudinal brake force. So smaller longitudinal force here. A rotation center is the center of a tire contact patch with the biggest brake force. I hope you can see the small dot here. This is a center of rotation. It's a bigger brake force than this one. In the second picture, this brake force is bigger than this one. So this is the biggest brake force here. And also you can see the small dot here. So the conclusion is that perfect car has a CG location on the longitudinal center line. Here we have a perfect car conclusion. CG location is important to prevent unwanted yawing motion. Rear brake force gets smaller when CG height gets higher. CG location offset from the longitudinal center line of a car makes a bigger yawing moment and the car gets unstable. CG location should be on the longitudinal center line of a car. And finally, CG location should be lower as far as it can. That's all, guys. Next video will be brake slip, the brake force distribution. See you at the next video. Goodbye, guys.